Namaskar, welcome all. Today's topic of discussion is power series solutions. So we are going to learn how we can use the technique of power series to solve differential equations. Here we are going to solve basically ordinary differential equations, and we are going to solve only for second order ordinary differential equation, and which is linear also. And so used to use series solution, power series solution, we are going to basically first learn what is power series and what is the convergence, what is the condition for convergence, what is the domain of convergence, and what is actually power series means. So, and we are also going to learn about power series about ordinary point and about singular point. So what is singular point? So we have basic idea from complex analysis what is singular point, what is ordinary point. So similar type of, actually same thing, but we are going to present in a different manner in the context of ordinary differential equation, and we are going to learn basically two different technique for power series solution for ordinary, around ordinary point and singular point. So what is regular singular point, that is also going to solve. So not all we are not able to solve by using power series for all singular point, only for regular singular point we can solve an equation. So with this brief, let's start. So power series and radius of convergence. In this power series, we are already familiar with the series of constant terms where summation of n and summation on 1 by 2 are 2 to the power n, and this type of series. So this is basically series of constant terms. We are familiar with that. And what is general power series? That is summation over a n x minus a to the power n. So power means that there is a the power, that means the summation over n, this n is in the power. So you can see a n is the constant and the power is that you can see x minus a to the power n. So you can see this summation over n, but n is in the power of this term x minus a. So this is the power series looks like. This is the definition of power series. So if we are able to present any function in this form, then that is called power series representation of these functions. So here an's are constant terms, and we are able to calculate it. Now this is the important remark that we should be aware of, that this when we are taking the summation, it is from 0 to infinity, but negative power is not allowed. So n is not negative here, the summation. So and what is the convergence of this power series? So already in the context of series of function, and then after sequence of functions, series of functions, and they are also in the context of analysis, we have learned power series solution, power series and convergence of power series. But here we are going to repeat basically with very little time that what is the convergence of power series. So already we can use we are going to use D'Alembert ratio test. We are going to use D'Alembert ratio test for the test of convergence of this power series. From the context of series, we know D'Alembert ratio test is one of the famous test to test the convergence of a series. So how do we do basically D'Alembert ratio test? We take a limit n tends to infinity. Here we have written limit n tends to infinity. In the upper you have a n, matlab nth term, that means nth term. In the lower you have a term of n plus 1, n plus 1th term. Okay, and then you just take the limit, and since after cancellation of the power, x to the power a minus n by x to the power a to the power n plus 1, we have this. So limit n tends to infinity, modulus of a n by a n plus 1, mod of 1 by x minus a. Now we from the theory of D'Alembert ratio test, we know if this ratio is greater than 1, then our series is convergence. If this ratio is less than 1, then our series is divergence. But if this series is equal to 1, we are indeterminate state. We are not able to comment about the convergence or divergence. But let's see here. So for convergence, we are looking for convergence. What is the domain of convergence? So for convergence, we need to have this ratio. I have just renamed R equal to just this limit. We have just given renamed it because in the next term, in the other term, we don't have any n. So limit is only operating on this first term. So I have given a name R. So the convergence if R by x minus a greater than 1, that means if mod of x minus a less than R. So this is our condition for convergence of the power series, and divergence in this, if this is less than 1, that means mod of x minus a greater than R. Okay, so this region x minus a minus R less than x less than a plus R, this region is called interval of convergence. And this R, because this R is the we are taking a small neighborhood of a with radius R. So this R is, that's why its R is called radius of convergence. Okay, and you can see from the series presentation x minus a to the power n. So this a, we have taken power series about the point A. So this is our power series. We are just little recap of the whatever we have learned in analysis theory. What is power series and what is radius of convergence? Let's see what is ordinary point and what is singular points of an differential equation. Here we start with recalling the definition. So basically from the theory of complex analysis, we know what is analytical functions definitions, but here we are going to present this definition in the context of Taylor series. So you may have learned this definition of analytic in the context of neighborhood of a point in complex domain, but here this function is a real function, and we are saying a function fx with the property that a power series expansion of this form, this is nothing but the power series expansion of fx. So if fx can be written in this form, then it is called power series representation. So if this is valid in some neighborhood of a point A, then we say the function fx is analytic at A. Basically, if you are able to write a function, if you are able to write the power series representation around a point for a function fx, then we say that function is analytic at A. And we already have seen when we are able to write this. We are able to write this only in the radius of convergence, that is mod of x minus a less than R. R is our radius of convergence. It is also called Taylor series of the function. So it will be called Taylor series if the coefficients are in this form: an equal to nth derivative of f at a by factorial n tends to 0 to n equal to n to 1 0 1 2 etc. So if you put this value at the coefficients, and then it will be Taylor series. Okay. So here the list what are the power series representation which are analytic. So this is the basic. We are not going to test all the time that what is the function analytic at a point. We already know the standard result about some function like e to the power x, sin x, cos x, and all polynomial functions are analytic at all points. And summation, multiplication, and fx by gx, where gx is not equal to 0 identically at any point. So if you just sum or multiply to analytic function or divide by another analytic function, then also their composition will be analytic again. And the sum of power series in analytic at all point inside the interval of convergence. Okay. So this is the standard result that we are going to use, because we don't want to test at every point is the function is analytic at a point or not. Okay. So what is called ordinary point? A point A belongs to some domain of the definition of the function, that is I, is called ordinary point if we are able to represent this function. Okay, so that we have seen analytic function. Now in the context of differential equation, let's see in the context of differential equation. So this is the equation on is our first second order linear differential equation standard form, where A0 is not equal to 0. A0x not identically 0. What will happen if A0x is identically 0? Then obviously the order of this equation will decrease, because if A0x is 0, then dy dx, d2y dx2 term will be vanished. So obviously it will convert to first order differential equation. We don't want to lose the order, so because that's why we have given the condition that the first coefficient of d2y dx2 is not identically 0. That means it is second order differential equation. Okay, so you can present at this is not identically 0, but just by dividing by this coefficient you can represent it in the form of 2. Okay, so when we are going to define ordinary point of a differential equation, so ordinary point of a differential equation is the coefficient px and qx are analytic. If these two functions are analytic at the point x equal to a, then we say that this point is ordinary point for this differential equation. Ordinary point is also called regular point of a differential equation. Okay, this is an example. Y double prime minus 2x prime plus 2py equal to 0, where p is a constant, is called Hermite's equation. This is a standard Hermite's equation we have taken as an example. You can see that x equal to 0, at x equal to 0, both the coefficient, the px here, px is minus 2x and qx is constant 2p. So both are analytic at x equal to 0. So x equal to 0 is the ordinary point for this equation. That means these two functions are we are able to write these two functions in the form of a power series. What is this function? Px and qx. Okay, let's see what is singular point. If a point which is not ordinary point, we call it as a singular point. Okay, that means at least one of them, px or qx, that is at least one of them is not analytic at x equal to a, then it will be a singular point. For ordinary point, both have to be analytic. For singular point, at least one of them is not analytic. Obviously that is a contradictory case. So this is if a point is not ordinary, then we will call it a singular point. What is called regular singular point, and why we are talking about regular singular point? Okay, so in the context of solution, why we are learning all this, we want to find out solution in the form of this series, power series. So this is a restriction in the theory that we are not able to find solution for all the singular points. So what type of singular points where we are able to find this solution? So there we are going to categorize it in the regular singular point. If this singular point has some extra property, some other things, okay, it is not analytic, but is there any other is there any good property? That means it is what type of singularity is there? So can we make it analytic by anyhow? So if we are able to multiply x minus a with px and x minus a's whole square with qx. So this is the definition where you see I have written it a on x by, so regular singular point, the definition of regular singular point, y double prime plus a1 by a2 a0 y prime plus a2 by a0 y equal to 0. Here what is px? Basically px is a1 by a0. Now if we multiply it by x minus a and if we multiply it by qx with x minus a whole square, that is a2 x by a0 x, if these two are analytic, so they are without the multiplication, that means only a1 x and a1 x by a0 x, p1 and q1, at least one of them is not analytic, but we can make them analytic by multiplying this power of x minus a. So we are multiplying x minus a with px and x minus a whole square with qx. If you multiply them, both the function become analytic. Both of them have to be analytic after this modification. Then we'll say this is a regular singular point, because we can regularize it. Ordinary point has another name, that is regular point. So we can make it regular by slight modification. That's why we are saying it regular singular point. Okay. Okay, so this is an example of regular singular point. You can see obviously x equal to 0 in the first equation, x equal to 0 is a singular point, and both of them are not analytic. Okay. Now if you multiply by x with px, what is px here? 2 by x, and what is qx? Minus 2 by x square. So if you multiply px by x and multiply x square with qx, both of them become constant, so both of them becomes analytics. So this is x equal to 0 is a regular singular point. It is singular point, but it is regular singular point. Okay. And in the Legendre equation also you can see x minus 1 minus x whole square. So what is x equal to plus 1 or minus 1. If you put x equal to plus 1 or minus 1 and divide it by, so if you write it in the form of px and qx, that means d2y dx2 plus px plus d2y dx2 plus pxy dy dx plus qxy equal to 0. Then you will see, so px and qx both are not analytic at the point x equal to plus minus 1. So x equal to plus minus 1 both are singular points here, but we can make it analytic by multiplying. So here also this is a regular singular point for Legendre equations, and similarly you can verify for Bessel equations. It is also regular singular point at x equal to 0. Okay, now let's see an example of how we can solve a differential equation by using power series technique about an ordinary point. Okay, so when you are trying to write the solution in the form of power series about what point? Ordinary point. Okay, this method is valid up to for only ordinary points. So what we are doing, we are writing yx, we are assuming yx can be written in the form of summation over m 0 to infinity cm x to the power m. This is our assumption. Okay, now we are going to trying to find out what is cm's r. Now here you have written this power series at the point origin x equal to 0. Okay, and at the point x equal to 0, and you can verify from equation on that x equal to 0 is an ordinary point. So obviously we can write it in the form. Okay, so how we are going to use it? You just take the first derivative and second derivative and put it the original equation. You will get the last equation. So from there you will equate the coefficients of x. We will equate the coefficient of x from both sides. Obviously in the right hand side all the coefficients of x are 0. Only 0 is there right hand side. So obviously coefficients are 0. So you equate it, you will get these relations. So after simplifying this relation, we are seeing we are able to calculate all the coefficients. Okay, here step by step the calculation are given. You can see by pausing it. Okay, next, so after the recurrence relation, from the equating the coefficients, we have gotten this recurrence relation. If we put all the values in the original solution, in the power series solution, then we will have this form, where all the coefficient except C0 and C1, all the other coefficient can be written in the form of either C0 or C1. So ultimately if you put, you can take common C0 into something plus C1 into something, what you can see here. So this is our final solution. Now you can see the term associated with C0 and the term associated with C1 are linearly independent. Okay, so for a second order differential equation we should have two linearly independent solution, and the general solution should be the linear combination of them, and you can see that is what we have gotten. So obviously whenever we are going to find out a solution about ordinary point, you will always get two independent solutions, and you will always get some non-zero C0 and C1. That means there will be only two constants, and all the other constant can be written either any one of them, either C0 or C1. This is the general format. Okay, now let's see what is the radius of convergence. Again, where you have taken nth term from this series, nth term, and by divided by n plus 1th term, and after calculating you can see this series converges for all s, because as r tends to infinity, this goes to infinity. So r is our infinity r. Okay, so r is infinity, so obviously the series converges for all x. So when r is infinity, obviously x minus mod of x minus 0, and mod x less than infinity. So obviously whole real plane is our domain of convergence. Okay, let's see how if it is not an ordinary point. So for ordinary point, only on simple technique, and we have described it with on single examples. Now if it is not ordinary point, it is singular point. Okay, so if it is only regular singular point, then we will able to solve it. But if it is singular but not a regular singular point, we have no technique till right now in our study, that we are not able to solve it by using series solution. Okay, so what is this method called? This Frobenius, due to the German mathematician who have given this technique, Frobenius method. Okay, so you can read the details about him here. Okay, let's go to the method. So consider the linear differential equation of order 2 of this form. So this is our linear differential equation. Here we have just described the method how we can. Again, we are going to take a trial solution here in the form of a series, but we are going to an extra term x to the power k. So if you see equation number 2, where we have taken a trial solution, you can see the before for ordinary point where we have taken a trial solution, or for a regular singular point we have taken a trial solution. The only difference is in the power of x. Here we have multiplied x to the power k and extra term. Okay, if you delete x to the power k, it will be for ordinary case. For regular singular point, we are taking extra term x to the power k. This is due to this method. We'll see why we are using when you are going to solve it. Okay, so again the technique is same. You take the derivatives and put it the original equations, and you equate with the coefficient of x on both side, and then solve it. And after solving it, you the lowest the coefficient. What is the lowest coefficient? If you see the series, what is the lowest coefficient of x? That is when you m equal to 0, so obviously x to the power k is the lowest coefficient of x. Okay, so if you equate the lowest coefficient, that means the coefficient of x to the power k both side, then you will get an equation, and we call this equation indicial equation. Why indicial equation? Because from this equation we basically get the value of k, because here we have again an extra unknown k. You can see an extra unknown k we have added here in the power series solution. Okay, so there are different cases for these roots, so for different values of k. So obviously this k will be a second order equation, so you will get two solution, two values of k, but here there are different cases. Why we have taken different cases? Because we have to find out two independent solutions, but if you put two different value of k, it is not always you will get two independent solutions. So how we can find out two independent solution? Okay, one solution, if you want to find out one solution, that is very easy. You just take the initial equation though. So you see the example, if the roots are so there are different cases. Today we are going to just discuss one case, that is if the roots are disjoint and do not differ by an integer. Okay, so do not differ by integer means if you take the difference of the roots, the values of the k, then they will not be, the difference will not be an integer. Okay, so here is an equation we have taken. Obviously x equal to 0 is a regular singular point, you can verify. Then we have taken the solution in this series form, and we have taken the derivatives, and you have put in the original equation. If you put in the original equation and then you equate the power of x to the power k in both sides, and you will get this initial equation, and from there you will value k equal to 0 and 7/3. Obviously you can see their difference is not an integer, so we can use this technique. What will happen if they are integer? That is a different case, but if this is the only case where if this is not the only case, but this is one of the case where for two different value of k you will get two different independent solution. Just put k equal to 0 and then solve it by same procedure. Use the recurrence relation by equating the coefficient of x on both sides, and you will get the relation between different coefficients, and you put them, you will get this solution. So you can see previously we were getting two coefficients and two independent functions solutions, matlab combination, in the combination of two terms c0 and c1, but here you have only c0. Okay, then another condition I have forgot to mention, that c0 is always non-zero. C0 cannot be 0 for Fibonacci method. For ordinary for solution of ordinary point, there is no such conditions. Okay, and if you put another value of k, you will get another solution, and ultimately if you take the linear combination, you will get the final solution. So this is the case. For we have just discussed one case. Okay, so this is the case for Frobenius, where the roots of the initial equations are disjoint, are different, but their difference is not an integer. Okay, that's all for today. Thank you. Namaskar.